Hey guys, welcome back to Earth Science. So today we're going to talk about the age of fossils and how do we know they're actually that old. So there's three ways I'm going to talk about. There are in actuality there's hundreds, not hundreds, but there's several different ways that scientists can use to date fossils. I'm going to talk about three, the big three. Stratigraphy is one of them. What stratigraphy is, it's layers of rock. So if in this picture, right, you could actually physically see the layers. And that's really how it is. You can see the layers of rock. If I were to draw lines between all the layers, I'd probably draw them like this. And then let's say we actually found a fossil in one of these layers. Let's say we found a fossil about here. And the good thing about this is that scientists actually know how old the layers of rocks are. They know that, let's say they know that this layer is 70 million years old. And then they know that this layer is 100 million years old. Well, then that would tell us that this fossil we found is somewhere between 70 and 100 million years old. They could also estimate that it's closer to 100 million years old because it's closer to that layer of rock. And that's really stratigraphy in a nutshell. The lower something is, the older it is, right? For example, let's say I have this aluminum can. I find it, and then I keep digging down, and I find a horseshoe. And then I keep digging a little farther, and I find a bone owl. How do I know which one's older? Well, the one that's deeper down is the older one, right? The one that's in the lower layer of rock. Now, when paleontologists go out and study these things, it's not always as straightforward as that. Sometimes it'll look like this. Sometimes the rock layers will look like this. And this is actually a majority of the time the rock layers may look like this. So how are they supposed to figure out which fossil is older now? Well, you can use a few methods. Let's say they find this pink fossil and they find this blue fossil. Well, how are they going to figure out which one's older? You can't actually figure it out by which one's lower, because the blue one actually looks lower in this case, right? The blue one's right here. It's lower than the pink one, but the pink one is actually the older one. How do I know that? Well, I know that because the pink one is in a lower layer of rock. All the way through this, H is always going to be lower than A. The reason this happens is because these rock layers, they get formed over hundreds of millions of years. And the Earth is a constantly moving thing. You have earthquakes, you have volcanoes, you have all sorts of things that shift the Earth. You have plate tectonic movements. You have all sorts of things that shift the Earth's movements. And so over time, this rock layer could get pushed up a little bit. These whole rock layers can get pushed down a little bit. And it'll tend to misshape, or you can have these like little cracks. So it'll tend to misshape a lot of the Earth. So it's hard to tell just based on how deep down something is. So what paleontologists have to do is they have to take samples of layers. They have to cut into the Earth, right, and pull out this sample. And then they cut into the Earth and then pull out this sample. And then they will see that, oh, this layer, this white layer is below the spotty white, the black and white layer, all throughout. So that the white layer has to be older than the black and white layer. So any fossil they find in this layer is going to be younger than any fossil they find in this layer. So this blue one is younger, believe it or not. I can show you another example. Let's say they find a blue guy up here. A blue guy up here, and then they find a pink thingy-me-do down here. And then they find a yellow thingy-me-do even farther down over here. Which one's older? I'll give you a minute to think about it. Correct answer is they're all the same age. The reason why I know that is because they're all in the same rock layer, right? This rock layer is slanted down due to the processes on the Earth, but I know they're the same age because it's the same layer of rock. All right, moving on. So that's stratigraphy. I guess you don't need my picture anymore, so I'm going to get rid of that. Okay, half-life dating is another way that we can tell how old a rock layer is, or how old a fossil is. So let's say I have this, ooh, no, I don't want yellow, let's do black. Let's say I have this fossil. Well, fossils, organic fossils, living fossils, are made of a substance called carbon-14. Now, there's a lot of radioactive substances out there other than carbon-14. Right? There's uranium, which is another half-life dating method. But typically for fossils, we like to use carbon-14. Because carbon is something that you find in your food every day. It's stuff that you eat. It's stuff that becomes a part of you. In living tissue, not everyone has uranium inside of them, but everyone has carbon-14 inside of them. Now, when you die, you're not getting any new carbon-14. So then at that point, once you die, the carbon starts to decay and starts to go away. And then let's say half of the carbon goes away. Right? Scientists actually know something very, very specific about this. Let's say you started out with 100 molecules of carbon-14. And then half, right, would be about 50. We ended up with 50 molecules of carbon-14, and then they found our fossil, right? How do they know how old that fossil actually is? Well, scientists know that it takes 5,740 years for carbon-14 to go away by half. So since we lost half of our carbon-14, scientists know that this fossil is 5,740 years old. Now, let's say another 5,740 years pass. Well, half of what's left will now decay into carbon-14. It'll always be half. Carbon-14 decays or goes away at a very constant rate. So now, instead of 50, half of that, now I have 25 carbon-14 molecules. And let's say 5,000, and that's another 5,740 years. So let's say another 5,740 years pass. Well, I lose half of my carbon again. And then at that point, I go down from 25 to, ooh, this is going to be rough, 17.5 molecules of carbon-14. And that's another 5,740 years. And it keeps getting reduced by half and half and half and half. Half, it gets cut in half again, it gets cut in. That's why it's called half-life. You lose half of the material that you have, and every time you do that, 5,740 years pass. So a scientist can determine how many times you lost half of your material, half of your carbon-14, and that will dictate how old that fossil actually is. And according to some very complicated math problems that I do not want to get into, that I was taught at some point but forgot at this point, you actually don't need to know how much carbon you even started with. Crazy. Wait, you look that up if you want, or I can talk to you. But you can ask me about it later, and I can actually explain it. All right. So another way, the third way I'm going to talk about is by using index fossils. Index fossils are very useful because layers of rock aren't very close together usually. Lots of times they're millions of years apart. Like this layer of rock could be 100 million years old, and this layer of rock could be 300 million years old. It's lower, right? So it has to be older. But let's say we find a fossil in this little layer over here. Let's say the fossil's like right here. Well, how old is that fossil? In reality, we have no idea how old that fossil actually is. We know it's between 100 to 300 million years old, but we don't know within that time, we don't know where it would be. That's 200 million years of a gap that we don't know. So in this case, we use something called index fossils. And index fossils belong to a species or an animal. Let's not use yellow. It belongs to a species or animal that was only around for a very, very small period of time. Like let's say like 20 million years. That's a lot smaller than the gap of 200 million years. So let's say that fossil is actually right next to one of our index fossils. And we know this index fossil was alive. Let's say we know this index fossil was alive at 250 million years ago. Well, we know that this pink thing we do now is pretty close to 250 million years, give or take 20 million years. So we know with a better accuracy the age of this fossil because of the age of the index fossil that's right next to it. And that is how we date our fossils. That's the end of the class. Bye guys, have a great day.